Welcome to the deep dive. Staying on top of everything happening in AI right now, it feels like, trying to keep pace with a rocket launch while simultaneously reading the instruction manual.
Yeah, it really does.
It's exhilarating, confusing, and things move incredibly fast. Amidst all this motion, one series of models has been steadily building momentum, especially, in the world of open-weight large language models, the Qwen family. And this deep dive is specifically for you, a listener who asked for a clear, step-by-step journey through the evolution of these Qwen models. You wanted to know how they've grown, the major steps they've taken, and, well, where they fit into the broader, rapidly changing landscape of AI development today.
Well, and our mission, based on the source material you've shared, which is a detailed technical paper on Qwen 2, and then a follow-up document covering the latest Qwen 2.5, is really to guide you through that evolution. We'll be sticking strictly to what's presented in these sources, unpacking the key technical advancements, the evaluation results, and sort of tracing the narrative of how these models have developed from their beginnings right up to their most recent, pretty powerful iterations.
Absolutely. Think of us as your guides through these, let's say, quite dense technical documents. We're going to start at the foundation with the initial Qwen models and Qwen 1.5.
Okay.
Then we'll take a significant leap forward into Qwen 2. We'll explore the architecture, the data, the training techniques that really define that generation.
Right.
And finally, we'll land on the latest and most advanced models, Qwen 2.5, and see how they push the boundaries even further. Along the way, we'll look at the massive data sets they used, the clever engineering under the hood, and how they stacked up against their peers.
Okay, let's unpack this.
So right from the start, the sources frame the development of the Qwen models within a really significant context. They place it inside this fast-developing world of large foundation models.
Oh, the kind of models that are so capable, they're contributing to what some researchers are actually describing as sparks of artificial general intelligence, or AGI.
Sparks of AGI, wow. That's a pretty bold statement.
It is a pretty high bar, yeah.
Yeah.
And it kind of sets the stage for the ambition behind the Qwen series, The journey, according to these sources, begins with the introduction of the initial Qwen series. This work is referenced as being introduced by a team back in 2023 that gave us the baseline models.
Got it.
From there, the progression continued, building upon that foundation, leading to the release of Qwen 1.5, which came out in early 2024. So we have this clear starting point and then a pretty quick initial iteration.
And what's fascinating, even at this early stage of the Qwen family, is that the sources mentioned they weren't just focused on text.
Right.
The Qwen 2 paper specifically points out that during the development of these early text models, they were also working on and released sibling models. Qwen VL, which is a vision language model, and Qwen Audio, an audio language model. That tells you the team was thinking multimodality model that can understand more than just text right from the get-go. They weren't just building text models. They were like building a family designed to perceive the world through different senses.
Exactly. It really does show a broader vision from the outset.
Okay, so we have the initial Qwen, then Qwen 1.5 expanding on that. The papers then introduce what they describe as the newest edition at that time, Qwen 2. This sounds like a major generational leap. What was the core foundation and structure of this Qwen 2 release?
Yeah, Qwen 2 is definitely presented as a significant evolution. At its heart, it's still built on the standard transformer architecture. That's the fundamental building block for most powerful LLMs today, right?
Right, the standard.
And it was trained using the next token prediction objective. If you're new to that term, it just means the model learns by constantly trying to predict the very next word or piece of text in a sequence. That's how it learns grammar, facts, and how to generate, coherent text. Now, the structure of the Qwen 2 release, as detailed in the sources, was quite comprehensive. It was really aimed at covering different needs. They released both foundational models and instruction-tuned models.
Okay, what's the difference there exactly?
So the foundational models are kind of like the raw engine. They've learned a massive amount of information from pre-training data, but they aren't specifically trained to chat or follow complex human commands.
Gotcha, the base knowledge.
Exactly. The instruction-tuned models, on the other hand, are fine-tuned on data sets of instructions and responses. That makes them ready for conversational interfaces and agent-like applications, much closer to what, a user would actually interact with. And they offered a range of sizes. For the standard dense models, they released 4 different sizes: a very small 0.5 billion parameter model, a 1.5 billion parameter model, a mid-size 7 billion parameter model, and then a large 72 billion parameter model.
Okay, pretty wide spectrum.
Yeah, but they also introduced a mixture of experts, or MOE model, in this release. This one had a total of 57 billion parameters, but here's the key difference with MOE. For any given piece of text or token it's processing, it only activates and uses a subset of those parameters, specifically about 14 billion in this case.
So the MOE model is like having a big team of experts, but you only call on the most relevant ones for a specific task, which makes it more efficient.
That's a great way to think about it, yeah. You have this large capacity available, but you're not paying the computational cost of using all of it for every single calculation. It's definitely more efficient during inference time. And the sources explain the rationale behind releasing these different sizes too. The smaller models, the 0.5B and 1.5B, they were explicitly designed with portability in mind.
Like for phones and stuff.
Exactly. The vision was for these to run locally on devices like smartphones, earphones, maybe even smart glasses, enabling AI capabilities right there on the edge. The larger models, the 7D and 72B, are aimed more at deployment across various GPU setups, from single powerful servers to massive cloud clusters. They cater to more complex and demanding tasks. It's kind of a tiered approach to accessibility and capability.
That makes a lot of sense, tailoring the model size to where it actually needs to run. So that's the lineup for Qwen 2. But, models are only as good as the data they're trained on and the engineering behind them. How did they actually build Qwen 2? What did that look like behind the scenes?
You're absolutely right. The data and architecture are fundamental. For Qwen 2, the pre-training data was, well, substantial. The sources state they used a high-quality, large-scale dataset comprising over 7 trillion tokens.
7 trillion. That just sounds like an enormous amount of information.
It is. It's a huge amount of text for the model to absorb. And this data covered a vast range of topics and languages, to give the model broad knowledge. But a crucial enhancement mentioned for Qwen 2, specifically compared to previous Qwen versions, was a deliberate focus on increasing the quantity and improving the quality of code and mathematics content within that data set.
Oh, that's interesting. So they weren't just adding more data, like indiscriminately. They were adding specific kinds of data, more targeted.
Exactly. And the paper suggests why they did this. They hypothesized that enriching the data set with more and better code and math would directly improve the reasoning abilities of the models, particularly in those technical domains.
Yep.
And this raises an important question for the whole field, doesn't it? How much does feeding a model specialized information in specific areas actually translate into it being better at tasks in those areas?
Yeah, does it really work?
Well, the Qwen 2 evaluation results later on, they provide a pretty strong answer to that. We'll get there. On the model architecture side, the dense models are, standard transformer models, but the MOE model had some specific design features. They incorporated both shared experts that any part of the input can potentially be routed to, and routing-specific experts, which are more selectively chosen.
Okay, so more flexibility there.
Right. It allows for flexibility in how different pieces of information get processed. They also used an interesting initialization technique for the MOE experts. They started from weights that were upcycled or sort of adapted from a dense model. Yeah, but to ensure the experts weren't all too similar from the start, they actually shuffled parameters around and even randomly reinitialized half of the parameters in each expert.
Huh. Why do that?
Well, the idea was to promote diversity among the experts right from the very beginning, potentially helping the model learn a wider range of skills or patterns, not just variations on the same theme. Another key focus for Qwen 2 was long context training. Being able to understand and reason over long documents or, extended conversations is critical for many real-world uses.
Definitely.
The sources mention they use techniques like extending the ROPE, that's rotary position embedding base frequency, using a method called ABF, or attention by finding during training. This basically helps the model maintain its understanding and performance, even when dealing with input sequences that are many thousands of tokens long.
So it's not enough to just see a lot of data. You also have to be able to process it in long chunks, keep track of it all. Makes total sense. Okay, building a powerful base model with trillions of tokens and clever architecture is one thing, but making it helpful, safe, and, good at interacting with people is another challenge entirely. That's where post-training comes in, right? How did they approach this for Qwen 2?
Precisely. Post-training is all about aligning the model with human preferences, making it useful for tasks like chatting, following instructions accurately, and crucially, avoiding harmful outputs.
Right, the fine-tuning.
Yeah, the core idea is learning from human feedback, and for Qwen 2, this primarily involved supervised fine-tuning, or SFT, and direct preference optimization, or DPO. DPO is closely related to reinforcement learning from human feedback, RLHF, which you've probably heard about.
RLHS is pretty standard now.
It is. It's a common way to teach models what's good or bad behavior based on human judgments. Their post-training data strategy for Qwen 2 was quite sophisticated. They used two main types of data. Demonstration data for SFT, which is simply pairs of instructions and correct or desired responses.
Like examples of good answers.
Exactly. And preference data for DPRLHF, where they have an instruction and multiple responses, and humans, or sometimes automated systems, indicate which response is preferred over the others. Now, the construction of this data involved two main steps, according to the sources: collaborative data annotation and automated data synthesis.
Okay, collaborative sounds like people. Automated sounds like machines.
Pretty much. Collaborative annotation was where human effort was heavily involved. It was actually a multi-step process. It started with automatically extracting task ideas. Then humans selected interesting and diverse instructions. Then came something pretty clever: instruction evolution.
Instruction evolution, what's that?
They actually used earlier versions of Qwen models to help make the instructions more complex or add specific constraints.
Wait, they used the AI models themselves to help create the training data to make the next version of the AI better. That sounds a bit meta, doesn't it?
It is a little bit recursive, yeah. It's a way to scale up the complexity and diversity of the tasks the model needs to learn. And then finally, human annotators evaluated and ranked responses generated by different models to create the final demonstration and preference data. A lot of human oversight there.
Okay, so humans are still very much in the loop.
Definitely. But even that has limits in scale, especially for certain kinds of tasks. So they also developed automated data synthesis strategies to generate a huge volume of high-quality training data without needing quite as many human annotators for every single piece. They had several pretty clever methods for this. For tasks with definitive answers, like mathematics, they used rejection sampling.
Rejection sampling.
Yeah, the models would generate multiple ways to solve a problem or explain a concept. They'd then check the final answer or the reasoning steps and only keep the examples where the model arrived at the correct conclusion through a reasonable path. They'd just reject the others.
So it's like having an AI tutor grade its own practice problems and only keep the A-plus papers.
That's a good analogy, yeah. It ensures quality for those complex, verifiable tasks. Then, for coding and instruction following with strict rules, they used execution feedback.
Execution feedback? Sounds like running code.
Exactly. For code generation, the model would write code, and then they'd run that code with test cases to see if it actually worked correctly. Yeah. And for instructions with specific constraints, like, say, write a sentence that starts with the and contains the word ephemeral, the model would generate a response, and they'd use Python scripts to automatically check if all the constraints were met. This automated testing ensures the model is genuinely following the rules, not just approximating. For more creative tasks, like writing fiction or role-playing, where objective correctness is much harder to define, they use data repurposing.
Repurposing how?
They took high-quality, publicly available text, like classic literature or detailed character profiles from somewhere like Wikipedia, and used the model to generate instruction response pairs based on that source material. It's almost like turning it into a reading comprehension task for the model. It helped train the model on creative writing and role-playing while keeping the quality and style aligned with established examples. And importantly, for safety and values alignment, they used constitutional feedback. They created a data set based on desired principles, like being helpful and harmless and things to avoid, like generating illegal or biased content. They trained the model using this constitution data to guide its behavior towards safer outputs.
So they built this whole automated pipeline to generate incredibly diverse and high-quality training data at scale. That sounds like a massive, massive undertaking.
It really is, but it's arguably necessary to train models on, trillions of tokens effectively and then align them properly. The actual supervised fine-tuning, SFT, for Qwen 2 then took over 500,000 of these examples, covering a huge range of skills instruction following coding, math, reasoning, role-playing, multilingualism, safety, the works.
500,000 examples just for SFT.
They trained the model on this data for 2 epochs, refining its ability to follow instructions. And the reinforcement learning from human feedback, RLHF, process for Qwen 2 had 2 stages. First, offline training using the collected preference data with DPO, And then an online stage where the model continually improved based on feedback from reward models that score its responses in real time, essentially.
Okay, constantly learning.
Right. They even mentioned using something called an online merging optimizer, which was an attempt to minimize the alignment tax.
Assignment text, what's that?
That's the idea that sometimes happens where aligning a model to human preferences, making it safer or more conversational, can accidentally hurt its performance on core tasks, like reasoning or coding accuracy. They were trying to avoid that trade-off.
Okay, deep pre-training data, clever architecture, and really sophisticated post-training with automated data generation and this two-stage RLHF. After all that work, how did Qwen 2 actually perform when they put it to the test? The paper has a lot of benchmark results, right?
It does, yeah, and the evaluation methodology was pretty thorough. They used a wide array of standard open benchmarks, plus some internal tests relying mostly on automatic evaluation. A key step they took, which is good practice, was a detailed contamination analysis.
Checking if the answers were in the training data.
Exactly. They checked rigorously if any of the test data might have accidentally ended up in the training data, because that can artificially inflate scores. Their analysis found that while there were some overlaps, often just common code snippets or basic math equations, it didn't significantly skew the results overall.
Okay, so looking at the base model performance, the big one is Qwen 272b. Comparing it to Llama 3 70b and its own predecessor, Qwen 1.5 72b, and even the larger Qwen 1.5 110b, Qwen 272b showed clear strengths.
Where did it shine?
It outperformed Llama 3 70b on general knowledge tests like MMLU and scientific benchmarks like GPQA. And importantly, it showed significant jumps in performance compared to Qwen 1.5 72b, especially in coding tasks, things like human eval and MBPP and in mathematics on GSMAK and math benchmarks.
Ah, those are the areas where they specifically added more high-quality data during pre-training, right? Exactly right. The results strongly support their hypothesis that targeted data enrichment works. It boosted performance specifically where they added that focused data. Its reasoning capabilities were broadly comparable to Llama 370b, according to the paper. And consistently, across tasks, Qwen 2 showed strong performance in Chinese understanding, surpassing both Western models like Mixtral and Llama 3, and its own predecessor, Qwen 1.5. The smaller models also held their own pretty well. Qwen 2 1.5b and Qwen 2 0.5b, when compared to peers like Phi 2 and Gemma 2b, showed superior performance in math.
Even the little ones were good at math.
Apparently so. Qwen 2 1.5b also did well in coding and language understanding compared to most competitors. And like their larger sibling, they were stronger in Chinese. Interestingly, Qwen 2 1.5b performed well on truthful QA, which measures how often a model hallucinates or just makes stuff up. Yeah, it suggests smaller models aren't necessarily more prone to hallucination than larger ones, which is sometimes an assumption people make. Okay, now moving to the instruction-tuned model performance. These are the models fine-tuned for chat, like Qwen 2 72b Instruct. They also saw big benefits from having that strong base model underneath.
Makes sense. A better engine makes a better car.
Exactly. Compared to models like Llama 3 70b Instruct, it generally outperformed in understanding, coding, and math benchmarks. But critically, it showed significant advantages on tests measuring how well models follow instructions and how well they align with human preferences benchmarks like MT-Bench, ArenaHard, and IFEVL.
So the fancy post-training worked too.
It seems so. This is credited to both the high-quality base model and the improvements in post-training data generation and the training techniques we discussed earlier. The MOE instruction model and the smaller instruction models also showed improvements over their predecessors and competitors, indicating that these benefits scale down effectively to smaller sizes too. The long context capabilities were also evaluated. Using techniques like rope extension with ABF and something called yarn plus DCA, the Qwen 2 models demonstrated a strong ability to handle very long inputs. The visual examples in the source material showing the model's ability to find a specific piece of information, the needle buried deep within a long text, the haystack, really illustrate this capability quite well.
Being able to find that needle is crucial.
Absolutely. Finally, the safety evaluation was conducted across multiple languages. They tested resistance to prompts designed to elicit harmful content jailbreaking attempts. Qwen 2 70b Instruct was apparently better at rejecting these harmful prompts than GPT-4 and Mixtral 8 by 22b Instruct in several categories. However, the paper is commendably very clear here. It states there's still much room for our model to improve, particularly in complex or sensitive areas like pornography. They acknowledge that safety is an ongoing challenge, not a solved problem.
Right. Transparency about limitations is good. So Qwen 2 represented a clear step up. It proved the value of targeted data enrichment, refined training methods, especially for math, coding, and alignment. But the story doesn't end there, does it? Building on Qwen 2, the next generation is Qwen 2.5. What's the big headline for this release? What
Oh.
changed?
Well, if Qwen 2 was about refined architecture and targeted data improvement, Qwen 2.5 is primarily about pushing data scaling to a massive new level. If you look at Figure 1 in the source material, it clearly shows the pre-training token counts. Qwen 1.5 was around 3 trillion tokens. Qwen 2 jumped to 7 trillion. And Qwen 2.5 makes this colossal leap to 18 trillion tokens.
18 trillion. That's more than double Qwen 2 and what, 6 times Qwen 1.5?
Yeah.
That sounds like the key difference right there.
It absolutely is presented as the key driver. The sources explicitly call this scale the reason Qwen 2.5 demonstrates the most advanced capabilities within the Qwen series. They highlight significant improvements, particularly in domain expertise. It really underscores just how crucial scale, probably combined with sophisticated data mixture strategies, is for pushing model capabilities higher and higher. The Qwen 2.5 release structure also expanded quite a bit. For the open weight models, they released a total of 7 sizes now: 0.5B, 1.5B, 3B, 7B, 14B, 32B, and 72B parameters.
There's even more options.
Yeah, and these are available in different formats for flexibility, like bfloat 16 and quantized versions, making them easier to deploy. They're released under permissive licenses like Apache 2.0. Table 1 in the source also notes that many of these models, especially the larger ones, come with significantly larger maximum context lengths, up to 128K tokens for the biggest ones.
128,000 tokens. That's a lot of context.
It is. Beyond the open weight models, they also introduced proprietary MoE models, named via their API as Qwen 2.5 Turbo and Qwen 2.5 Plus. These are stated in the source to be highly competitive with well-known proprietary models like GPT-4 Mini and GPT-4o, respectively. And here's one of the most remarkable claims from the Qwen 2.5 source material. The open-weight flagship, Qwen 2.572B Instruct, performs competitively against Llama 345B Instruct.
The 405 billion parameter Llama 3.
Yes, which they note is around 5 times larger than their 72B model.
5 times larger. So they're claiming their 72B model, by virtue of this massive data scale and other refinements, can perform as well as a competitor's model that's 5 times bigger.
That sounds incredibly efficient.
And true.
That's precisely the claim they make, and it highlights a key potential insight. Scale isn't just about model size, it's also hugely about data scale and quality. Getting that right might lead to incredible efficiency gains and higher performance ceilings, potentially allowing smaller models to challenge much larger ones.
Okay, 18 trillion tokens is the headline. Huge data increase. But was it just adding more data, or did they refine the building process further for Qwen 2.5? Did they learn lessons from Qwen 2?
Oh, it was very much an iterative refinement process, building directly on the foundation and learnings from Qwen 2. The expanded pre-training data to 18 trillion tokens was, as we said, a key factor, focusing on both quantity and quality across diverse domains, presumably building on the successful strategies from Qwen 2. They also got more sophisticated with using scaling laws. Using data from Qwen 2.5 itself during development, they developed scaling laws not just to figure out optimal model sizes, but also to determine the best training hyperparameters, things like batch size and learning rate schedules for different model sizes and architectures, both dense and MoE.
So using the model's own learning curve to optimize its training.
Kind of, yeah. It allowed them to guide their training configurations more effectively and even predict performance more accurately during the long training runs. Long context pre-training continued to be important. They use a two-phase approach, again, extending context during training. The techniques like ABF on root E base frequency were used, extending it to a base value of 1 milsin for extremely long contexts like those handled by the Turbo model, though the open models were pre-trained up to 32,768 tokens. They also significantly enhanced their post-training methods, building on that already sophisticated Qwen 2 framework. They used a refined two-stage reinforcement learning process.
How was it refined?
The offline RL stage specifically targeted complex abilities like reasoning, factuality, and hard-to-evaluate instruction following, using meticulously validated, high-quality data. The online RL stage then leveraged the reward model for more nuanced quality aspects like truthfulness, helpfulness, conciseness, relevance, harmlessness, and debiasing, using more immediate feedback. This split allows them to train different types of desired behaviors more effectively, the really hard stuff offline, the nuances online.
Splitting the RL like that makes a lot of sense. Using carefully checked data for the really complex stuff and the automated reward model feedback for the more subtle refinements seems logical.
Exactly. They also strengthen instruction following validation even further with what they call a rigorous code-based validation framework.
More code.
Yeah, this sounds like another level of automation on top of Qwen 2. The LLMs generated instructions, and the verification code or unit tests needed to check if the response actually met the instruction's requirements. They used execution feedback running the code, combined with rejection sampling, to curate the SFT data with incredible precision. It's a highly automated way to ensure the model learns to follow instructions really, really precisely. To boost specific capabilities, they developed dedicated datasets and methods. They created a comprehensive structured data understanding dataset, incorporating reasoning chains into responses to help the model infer information better from structured data like tables or lists.
Making it better with data that isn't just plain text.
Right. For logical reasoning enhancement, they introduced a large, diverse set of 70,000 new queries covering various types: multiple choice, true, false, open-ended. They specifically trained the model to use a range of reasoning methods: deductive, inductive, analogical, causal, statistical. And again, they used iterative refinement to filter out bad data examples. For multilingual capabilities, cross-lingual transfer involved using translation models to create instruction response data for languages with fewer existing resources, while carefully evaluating that the semantic alignment, the meaning, and style were preserved across languages.
So trying to bootstrap performance in more languages.
Seems like it. They also built robustness to different ways users might phrase things by constructing hundreds of diverse, general, robust system instruction prompts for training, aiming for more consistent behavior. And for the final output quality, response filtering was described as particularly rigorous. They employed multiple automatic annotation methods, including a critic model and even a multi-agent collaborative scoring system, retaining only responses deemed flawless by all scoring systems for the highest quality preference data.
Flawless according to multiple AIs. That's a high bar.
It really is. Just a bit more detail on the online RL. The reward model was trained on data from public and proprietary sources. Responses were generated from many different model checkpoints and using different methods and temperatures to get variety. Preference pairs came from both human and automated labeling, plus DPO data. They used a technique called Group Relative Policy Optimization, GRPO, and apparently prioritized training on queries where the model's responses varied the most in quality, trying to improve consistency where it was weakest.
Focusing the learning where it's needed most.
Right. And they noted that even though they trained RL mostly on shorter instructions for efficiency, the benefits transferred well to long context alignment, too.
That's an incredibly detailed and sophisticated training pipeline. It's clear they weren't just dumping more data in for Qwen 2.5. They were really building on their previous work with highly refined techniques at every stage. So with all that effort, especially that huge 18 trillion token data jump, how much better is Qwen 2.5 on the benchmarks compared to Qwen 2 of the competitors?
Okay, the evaluation approach was consistent with Qwen 2, a wide suite of benchmarks and those careful data leakage prevention checks. Looking at base model performance, the effect of that 18 trillion token dataset is pretty undeniable in the results presented. Comparing Qwen 2.572b to Llama 370b, Mixtral 8x22b, Llama 3405b, and its predecessor, Qwen 272b, in Table 2 of the source, well, Qwen 2.572b shows substantial performance improvements over Qwen 272b across many benchmarks. We're talking significant jumps in MMLU, MMLU Pro, GPQA, Math, and MBPP.
The big general knowledge, science, math, and coding benchmarks.
Exactly. It clearly pulls ahead of Llama 370b in these areas, according to these results. And the proprietary Qwen 2.5 Plus also performs very strongly, as you'd expect. For the medium-sized models, like the 14b and 32b variants in Table 3, Qwen 2.5 14b holds its own well against competitors. Qwen 2.5 32b in particular is described as showing exceptional capabilities, often beating larger models from other families and significantly outperforming its Qwen 1.5 32b predecessor, especially again in math and coding. That targeted data focus seems to scale. The proprietary Qwen 2.5 Turbo is also shown as competitive despite its lower cost profile. The 7B model, Qwen 2.57b, compared to Mistral 7b, Llama 3.8b, Gemma 2.9b, and Qwen 2.7b in Table 4, also surpasses its predecessors and counterparts across numerous benchmarks. Again, notable advantages in math and coding. Even with potentially fewer non-embedding parameters than some peers, the refined data and training seem to make a big difference.
So the benefits are seen across the size range.
It seems so. And the smaller models, Almond 0.5b, 1.5b, 3b, and Table 5, also show substantial performance improvements over their Qwen 2 versions. Qwen 2.53b, for instance, performs well against models like Phi 3.5 Mini despite being slightly smaller in parameters. These improvements make the smaller models even more viable for running on edge devices, and the sources attribute this mainly to that pre-training data scaling. Okay, moving to the instruction-tuned model performance. Here we're looking at models like Qwen 2.572b Instruct and Qwen 2.5 Plus in Table 6, compared against things like Llama 3.170b 405b Instruct and Qwen 272b Instruct.
How does the flagship instruction model compare?
Qwen 2.572b Instruct shows strong performance overall. Significant improvements over Qwen 272b Instruct are noted in areas like math, coding benchmarks like Live Code Bench, and those crucial instruction following and preference alignment tests like Arena Hard and MT Bench.
So the improved post-training pipeline really paid off there.
It seems to confirm that, yes. It stands very competitively against the Llama 3.1 variants according to these tables, especially considering the size difference with the 405b model. Qwen 2.5 Plus also performs strongly. The other Qwen 2.5 Instruct models, like the 7B, 3B, and smaller ones, tables 8, 9, 10, also show significant advantages over their predecessors and competitors. Qwen 2.5 7D Instruct notably outperforms its 7B competitors across most tasks, with clear advantages again in math and coding. The smaller instruction models also see marked gains, attributed mainly to that big data jump in pre-training, providing a better foundation.
How about multilingual performance for the instruction models?
Yeah.
You mentioned the base models were strong in Chinese.
Right. On multilingual evaluation, tables 11, 12, the Qwen models, especially the Qwen 2.5 Instruct variants, continue to show very strong performance in Chinese, clearly leading compared to Qwen 1.5 and Llama 3.1 in the presented results.
Yeah.
In English, table 11, they are competitive, but the sources do note they might slightly trail top models like Llama 3.170b Instruct in some specific comprehension or coding areas.
Okay, so maybe a slight difference in emphasis.
It could suggest differences in the language mix or the distribution of specific task data within the pre-training or post-training datasets compared to competitors. Hard to say for sure without seeing the data recipes.
What about handling long texts? That was a focus for Qwen 2. Did it get even better in Qwen 2.5?
Yes, long context capabilities for Qwen 2.5 were also evaluated extensively, table 16, 17, using benchmarks like Ruler, LV-eval, and Long Bench Chat. With their DCA plus Yarn techniques, the models demonstrated strong, long context processing capabilities. A key finding highlighted in the source is that Qwen 2.572b Instruct shows the strongest performance across all context lengths, evaluated among open-weight models.
Strongest among open models. That's impressive.
The paper states it significantly outperforms existing open-weight long context models, as well as the proprietary models like GPT-4 Mini and GPT-4 on these specific long context benchmarks. This is presented as a major strength. The evaluation also includes ablation studies showing a clear performance drop if you don't use these long context techniques like DCA plus Yarn, proving their effectiveness. And they even evaluated their reward model, the model used to guide the RLHF process for Qwen 2.5, table 15. While it showed competitive scores on benchmarks like Reward Bench and RMB, the sources make a really crucial observation.
What's that?
They state that current reward model evaluation benchmarks do not accurately predict the performance of the RL models trained under their guidance.
That's a fascinating note. So it suggests that even if a reward model looks good on a benchmark test, it might not actually be the best guide for training the final instruction following model in practice. It points to a potential gap in how the field currently evaluates these alignment tools.
Exactly. It's an important insight about the limitations of current evaluation methods, even while the models themselves, and likely the reward models too, are improving. It highlights an area needing more research.
Okay, so we've traced this whole path from the initial Qwen models through Qwen 1.5, then the significant technical advancements and targeted data improvements in Qwen 2, leading all the way to the enormous data scale and highly refined post-training of Qwen 2.5. What does this whole evolution tell us about where the Qwen series stands in the big picture of language model development right now?
Well, it definitely paints a picture of rapid iterative progress. The journey is fundamentally driven by scaling. That jump to 18 trillion tokens for Qwen 2.5 is immense and clearly yielded huge performance gains according to their evals. But it's not just about brute force data scaling. It's combined with refined architecture choices, both dense and MoE, and increasingly sophisticated training and post-training techniques. Those automated data synthesis methods, the multi-stage RL, the code-based instruction validation, they're all crucial parts of the story.
Right, it's scale plus smarts.
Exactly. This positions the Qwen series as some of the most competitive open-weight models available today, based on these sources. They are actively pushing the state-of-the-art and, as the papers highlight, challenging the performance of even much larger or proprietary models in many key areas. Their particular strengths, as shown repeatedly in the benchmarks, seem to lie in mathematics, coding, Chinese language tasks, and demonstrating truly leading capabilities in long context processing among open models. Their contribution to the broader field is also significant. By releasing these model weights openly on platforms like Hugging Face, ModelScope, and GitHub, they make powerful models accessible to researchers and developers worldwide.
Fostering innovation.
Right. It allows the community to build on their work, verify results, and explore new applications. And their detailed technical papers also share valuable insights into the practicalities of scaling, the intricacies of data curation, effective post-training strategies, and even the nuances of evaluation, like those limitations they observed in reward model benchmarks. That helps everyone learn.
Bring it back to that initial idea from the sources about sparks of artificial general intelligence. How does this journey, this relentless push for scale, the refinement of capabilities across so many different tasks and languages, the ability to handle incredibly long contexts, how does that contribute to that larger conversation about AGI?
I think it shows that these key areas, scaling data and model size intelligently, improving data quality and targeting it effectively, and continually refining the training and alignment processes are indeed the primary pathways the field is taking towards developing models that are more capable, more general, and more robust across a wider range of tasks. Each leap, particularly the sheer scale of Qwen 2.5 and the sophistication of its entire training pipeline, adds more evidence to the idea that we are seeing models gain increasingly complex and general abilities. They're contributing to those sparks of AGI the sources mentioned, even if true AGI is still, a long way off.
Wow, that really was a deep dive into the evolution of the Qwen models. From setting the foundation with the initial series in Qwen 1.5, through the significant architectural and targeted data improvements in Qwen 2, to the impressive data scaling and refined training of the Qwen 2.5 generation. It's a really clear story of iterative progress, boosting performance across tasks, sizes, languages, and tackling important challenges like long context and safety.
Indeed. And the sources also offer a little glimpse into what the Qwen team is looking at next. They mention plans to continue refining models with even broader and higher quality data, which seems inevitable.
Always more data.
Always more data, but also integrating various modalities, text, vision, audio, into a single unified framework for more seamless understanding of the world, and further enhancing reasoning capabilities, especially by optimizing the compute resources needed for inference, making complex reasoning cheaper to run.
That leads us to a final thought for you, the listener, to consider. If scaling data to 18 trillion tokens and refining training techniques, this much can enable open models to compete with proprietary giants 5 times their size, and make powerful AI accessible even on small devices. Well, what previously unimaginable capabilities might emerge as these models continue their scaling journey and become truly multimodal, seamlessly understanding text, images, and sounds all together? What new sparks might we see then? Thanks for joining us for this deep dive into the Qwen series. We hope this exploration has given you a clearer picture of their development and their significant place in the fast-moving world of large language models.